All right, thanks. That was great. Yes, I'm going to have a problem in my family. I'll get myself a Panther Lake, and then the kids are going to argue about who gets the Lunar Lake next. So that's going to be a fun argument to have. I'm Stephen Robinson. I'm here to talk to you about compute and the CPUs that we've done in Lunar Lake. So as CPU architects, right, the very first thing we need to do is target the process node that we're going to build the product on. So supporting a transition to 18A was our first priority. You know, that includes libraries, PDKs, and we want to make things a foundry-like experience. So we wanted to work with our manufacturing partners and make sure that our experience and other people's experience would be good. So that was one of the things we wanted to focus on. Also, for Panther Lake itself, we wanted to look at more cores, as Eric showed. You know, we increased the number of cores on there, so we wanted to do that in a balanced, efficient way. Wanted to right-size the compute. We wanted to make sure we have efficient compute, area, power, performance, and merge that Lunar Lake and Arrow Lake experience into a single product. So first, our CPUs, right? As we've talked about, we have hybrid compute. We've been doing this for many generations. You know, we started it in mainstream back in Alder Lake and Raptor Lake and Meteor Lake, et cetera. So we wanted to continue that and improve the overall dynamic behavior. So, you know, there's the SoC, there's how many cores we build, there's what we build within the cores, there's the core count, there's scheduling, right? There's a lot of work that goes into making sure that we're doing the right balance of power and performance for a variety of workloads. So that was our goals and our journey. So let's talk about our CPUs. So Ark mentioned it. We've got P cores and we've got E cores. So Cougar Cove is the name for our next generation performance core, our P core. A P core will always be incredibly important to products, right? That's what drives that experience, that performance. You know, when you want when you ask your computer to do something, you want to do it quickly. That's what the performance core is for. But also, you know, we've got more evolving workloads, games, everything. Everybody's using more cores. So we can't put just one P core. We put 4 in this product, which is excellent. And then we're now fleshing it out with those E cores. The E cores have 2 roles to play. The first role is to have more multi-threaded performance, more throughput, so that when you're doing content creation or you're playing games, you have all the CPU throughput that you need. The other side is on low power and efficiency. So the more cores you have, the more power that you have to manage. And when you're doing less with your laptop, right, we've talked about containment. We have E cores in that low power island. Arik just showed you kind of how they connect, where we can get them closer to memory with a little bit of cache. And that's what leads to the all-day computing that Lunar Lake brought to x86, and Panther Lake continues to improve. So I touched on this. We have a hybrid journey. So starting with Meteor Lake is the first time we brought 3-way hybrid. That's where we started our low-power island journey. The low-power island in Meteor Lake was good, but insufficient. Right? We had 2 cores. They didn't have much cache. They weren't quite as quick. They couldn't go to a high frequency. They didn't have dedicated power delivery. In Arrow Lake, we continued down that path, but we upgraded our MT throughput cores, those E cores, right? We moved to the SkyMont base microarchitecture. And so that was a great improvement on performance, but it didn't necessarily bring that all-day battery life. Lunar Lake, on the other hand, did make those changes. We had dedicated power for the E-core. We had additional cache. We had more cores. And we could go to more frequency because we had a dedicated power rail. So, but Lunar Lake, we didn't have additional E-cores for MT throughput. So that's Panther Lake, right? That's the simple pitch, right? It's really straightforward. Low power island, enough cores for that throughput, and next generation P cores for that single-threaded performance. You put that all together, and you get Panther Lake. So 18A, transition, I'm an architect. What does any of this mean to me? Well, when we build a new CPU and a new process technology, there's a new library, there's arrays, there's custom circuits, there's PLLs, there's temperature sensors, there's all of these little individual things. And every time you go to a new process technology, you have to prepare for all of that. So you need to get your libraries together, and you need to get your arrays together and all of your custom circuits. So we did all of that specifically targeting 18A. Now, you've heard last night in the keynotes about PowerVia, this backside metal implementation. That changes the libraries. Today, libraries typically have power, embedded into each library cell. You construct it, and it's a grid of power. That's gone. That's different. The rules for building the library are different. The rules for assembling the library are different. That gives us density. Power delivery is significant. It's a lot of wires. It's a lot of resources. It's a lot of tracks. Now those are gone. Those are connected through the back. We no longer have those in the areas in the critical cuts of our CPUs. So that leads to density. That also improves the power delivery. So because you're putting it on the back, you can dedicate more resources. It's no longer fighting for that area with the signal routing. And so you end up with a more robust power delivery, and that more robust power delivery reduces the losses in there, which turns into reduced voltage droop, resistance on that network. It created an oddity. So, since I've been designing CPUs, since I've been working in the industry, we've always had power available. When we have power available, we like to shield things. Power is a way to keep signals from attacking other signals. So that is good for noise and stability of high-frequency signals. I have a clock. I want to ensure the clock is well shielded. I want to make sure nothing can attack it. That gives me reliable performance and experience, and I can achieve high frequency. I lost that ability. So here, we have to do something else. So this is where we end up doing width and spacing of wires, where we can spread things out. We make sure we're not routing things next to each other. It's not terribly complicated. It's just a change. It's a side effect of the new process technology. So these are the kind of things we had to do in our microarchitecture and our physical implementation to support the transition to 18A. OK, Cougar Cove. This is our next generation P-core. We introduced Lion Cove in Arrow Lake and Lunar Lake a year or more ago. And Cougar Cove builds on top of that. What we wanted to do was we wanted to take the excellent fundamentals that Lion Cove brought. We wanted to target 18A. We wanted to optimize it. We wanted to build on that fundamental. So we didn't go in and change the width. We didn't change the depth. We optimized. Lunar Lake in Lion Cove had, say, a 12 meg L3. Well, here we get a 50% larger L3 because of the addition of the E-core cluster and the way that our fabric scales. So now you've got 50% more L3 cache. But again, it's kind of built on that same baseline. We also brought in improvements for heuristics. You're going to hear that a lot, right? Our workloads are dynamic. The way you use machines is dynamic. You're doing lots of different things at different times, and you want the system to react. So our power management has to evolve to understand those workloads. We take telemetry, we make decisions. And same thing for prefetching and aggressiveness. Prefetching is a way to bring performance. Here, we're continuing to evolve and making that dynamic. That brings more reliable performance. So I say optimization, right? Again, this isn't a massive change. This is evolution. This is efficiency. So we did three major things. We did many more than three things, but these are the three things that we're focusing on. The first is memory disambiguation. So when I am executing a program, there are loads and stores. Sometimes they're connected. Usually they're not. And we have enhanced our ability to predict when a load and a store are connected, and use that information to schedule the load correctly. When we get that right, you get increased IPC. you get increased performance. You get more predictable and reliable performance. So your programs run a little bit faster and a little bit more effectively. The second thing is, again, workloads are getting more complicated. So our TLB, this is what caches translation, does security checks, et cetera, to make sure that you're executing the program the way you're supposed to. We grew capacity, right? 18A gave us the ability in the budget to grow some structures, and the TLB was one of the primary ones. We did this, again, so that complicated workloads run faster and more reliably. Finally, branch prediction. I doubt there's ever been a CPU disclosure where somebody didn't stand up on the stage and say, I made branch prediction better. So, of course, we did that as well. To zoom in on branch prediction a little bit, Lion Cove actually was a meaningful change in how we do branch prediction. We changed kind of some of the algorithms, the way that we index into things. This gave us the ability to have more capacity and predict more quickly. So in these modern superscalar out-of-order processors, we need to predict quickly, and we need to predict the next branch, even if it's far away, quickly. Lion Cove brought optimizations that helped exactly in that area. So it was our first generation of it. Cougar Go took that, took post-silicon learnings, things that it weren't perfect at, and we continued to evolve. So we've changed some underlying algorithms to be more accurate. We grew capacity. So we have a multi-level predictor, and as you grow capacity in the first level, or the second, or the third, that shortens the latency to the prediction. It covers bubbles. It's faster. It's lower latency. So we grew some structure sizes. The other thing we did was we grew some of the sort of metadata, the prediction. Am I likely to take this branch? Am I not likely to take this branch? And we made some of that deeper. So the net is shorter latency, more prediction bandwidth, and more prediction accuracy. Prediction accuracy and capacity together is significant when it comes to energy efficiency and performance both. It's a double victory because I spend less time doing wasteful work and more time doing useful work. So that's energy and performance together. Okay, so those are the types of optimizations that we did on the P-core. The E-core story, Darkmont, is, I'm going to tell you a similar story. We brought Skymont to Arrow Lake and Lunar Lake, and in Lunar Lake and the Low Power Island. Skymont was a significant upgrade over Crestmont, the previous generation. We're building on that foundation again. 26 dispatch ports, that's the same as Crestmont. More vector throughput, that's similar to Crestmont. More L2 bandwidth, that's similar to Crestmont. But we continue to evolve and optimize our CPUs. So we have things like nanocode, which we brought to in Skymont. Now we have more effective nanocode. And prefetching, right? I talked about dynamic AI-based prefetching on the P-core side. We have similar technologies on the E-core side, where we have made the prefetching aggression, the levels that we shoot for, dynamic. As we get telemetry, we decide whether we want to do more or less. So for the E-core, again, we've got 3 or 4 different things that is what we brought to the table. Again, it's a similar story on branch prediction. We made some algorithm tweaks so that we were more accurate. We brought modes where we can predict and shut down the front end. Loop stream detection, we can now do that as of Darkmont. This saves energy and gets you that more reliable performance. Nanocode. So nanocode's weird. As far as I know, the Intel E-core is the only processor that does the equivalent of nanocode. So microcode is something that x86 and other processors have done for a very long time. When you have complex instructions, sometimes you have to generate many, many UOPs for that. We do that through what we call microcode and a microcode sequencer. It's a big ROM that we have on our chip that does complicated instructions. Nanocode is where we've taken some of those and we've embedded them into hardware, into PLAs, into the front end, and we have the ability to decode microcode UOPs, nanocode in this case, And we can do that in each of our parallel front-end clusters. Starting in Skymont, we had 3 different parallel front-end clusters. So we can actually do the equivalent of parallel, out-of-order, microcode-like sequences. We save latency, we save bandwidth, we save area by doing this, and we get performance. So in Darkmont, we have more cases and more optimized cases that we can simply do through nanocode, and we can now leave the microcode sequencer alone. And again, memory disambiguation. This is a technology where, the E-core architects, the P-core architects, they work together, they share, and we end up putting in novel, unique things, and we're solving similar problems. Okay, Panther Lake. Performance, right? Already mentioned this. So here I'm showing, right, we have 2 baselines to compare against because this product is the superset of the previous 2, so Arrow Lake and Lunar Lake. So performance versus power, 40% lower power at similar performance. So, 18A, the Cougar Cove optimizations, the SoC platform, this is SoC power. So all of the great work that Arik and his team have done to lower overall SoC power is all part of this picture. This is the performance you get. At the similar power level, 10% more performance. So again, that's a snappier, more effective device, and at lower power when you are not needing the full peak. Multi-thread. This is a fun chart. 50% more performance at similar power. So Lunar Lake was designed to optimize sort of a 15-ish watt thing. So it had 4 P-cores, 4 E-cores in the low-power island. Now that we brought E-cores onto the compute tile, and we can go up to 16 cores, you see this significant update, this improvement in multiprocessor performance. And again, you put all this together, 18A, CPUs, the SoCs, 30% lower power at similar performance versus Arrow Lake. Okay, so new E-core, new P-core, Cougar Cove P-core, Darkmont E-core. How do we build them? How did we instantiate them? Where do we come from? So Lunar Lake, as Arik mentioned, there are multiple versions of Lunar Lake. We've got the 8-core version. So this looks similar to Lunar Lake. So we've continued to bring that with a more flexible platform so that you can integrate things. The OEMs can integrate things differently as needed. But you have that same 4+4. That's the laptop my kids are going to argue about, right? My Lunar Lake laptop is the one that they're going to fight over because, does the college age one need more battery life, or does the high school one need more battery life? I don't know. They'll fight it out. And then Panther Lake, right here, we've got the 16-core, where we've added those 8 E-cores onto the compute tile to get that MT performance that I showed you. So again, this is kind of hitting on what Arik had talked about, the caching and fabric, right? So our story is first low power island, 2 Crestmont cores, 2 Meg L2, no system cache. You come to Skymont in Lunar Lake, and you get now 4 cores, double the core count. You get a 4 Meg L2, double the L2, and you add an 8 Meg system cache. So you also have dedicated power rail. With that dedicated power rail, now instead of stopping at, I don't remember specifically, 2.5 gigahertz, in Lunar Lake, we took it up to 3.5 gigahertz or more. That's coverage. That's containment. That's more workloads running in a more efficient operating point. And then finally, you've got those 8 cores on the ring. Adding the cores to the ring brings more cache. Now you got that 18 Meg L3, that LLC, that ring. And that is not just performance, but that's performance and latency and capacity and power efficiency. Again, my favorite feature in the universe is a cache. It saves power, it improves bandwidth, it reduces latency. There's just cost associated with it. That's why we don't just throw more and more at it. But I love cache. Okay, so that's the IP and that's the SoC construction. So now I would like to bring Rajshree up here, and she can talk about scheduling and software. Thank you very much.
Thank you, Steven. Good morning, everyone. I hope you are really enjoying all the Panther Lake talks about SoC and architecture and things. My name is Rajshree Chabukswar. I am a software architect at Intel, and I'm going to talk about expanding on what Arik and Steven started, how we do scheduling, how we do some of the platform software optimizations, as well as our power management firmware optimizations to take advantage of our new cores and new SoC. So before we go into scheduling, let's start with what we had kind of shown you guys with Alder Lake, when we started Alder Lake, a technology called as Thread Director. And really kind of taking a step back on why we needed something like Thread Director was, as Steven talked about, we have two different microarchitectures, the P-core and E-core. Even though the instruction sets and capabilities are same between them, the performance and IPC, as we talk about, is different, right? Because we have different caches, different size of caches, TLBs, internal resources. So we had to make sure that we guide operating system. This is not a hard rule that we move anything behind the scene. Ultimate decision is with operating system, but we guide from our side on which one is the most performant core to be used in certain cases or which one is the most efficient core. So that's where we started Thread Director. It has two components. The first one is the core side. And what core side does, this happens on both P and E cores, is it basically uses a lot of internal telemetry to classify the set of instructions being executed into 4 different classes that we have. Class 0, which is like scalar typical instructions where IPC is similar between P and E cores. Then we have class 1, where we get slightly better IPC with P cores. Then we have class 2, where some of the AI, CPU-based AI-specific instructions can deliver higher IPC. And then we have class 3, which is non-scalable work, right? So that part is one of the ones that we have from the core side. The second part of it is the SoC side or P-code side, where we have hardware feedback interface table. It's called as HFI table, and it's documented in our SDM as well. That provides an ordered list of which ones are the most performant cores and which ones are the most efficient cores. Operating system reads this table, and in case of any major changes, let's say some power thermal event shift happened, OEM decided that, hey, I want to go to 10 watt of PL1, and I'm running some GPU task, I'm running some NPU task, CPU task. So internally, we have power adjustments, right? Power balancing that we do from our P-code side. So in that case, if power to codes reduce, and we have to change ordering of which one is the most performant or efficient core, then the table updates happen. And we send an interrupt to operating system at that point to read that table as well. Now, operating system uses this information. Again, this is a guidance that goes from hardware to OS. OS uses this information along with its own goodness. So OEMs can select what is the scheduling policy I want. Do I want to start with performant cores first? Do I want to start with efficient cores first? And it uses all of that information along with what Thread Director provides to come up with better scheduling decisions. So let's talk a little bit about Panther Lake on what's new here in Thread Director, right? As Steven talked about, we have a lot of microarchitectural improvement that went into both Cougar, Cove, and Darkmont, the RP and E-cores that are launching with Panther Lake. Which means that with new IPC deltas, we have updated our classification models, and we have provided optimal support for giving guidance to operating system. We had to go do that because we can't use our old classification model since microarchitecture and improvements has happened, right? So there's a lot of work, internal work with newer telemetry added, retraining, etc., to make this happen for Panther Lake. We have also done some power management improvements, and we'll cover them in the next few slides. Thread Director is our way to communicate any recommendations that have changed to operating system. That's our major interface, right? If ordering of cores changes, if graphics is taking more headroom, and we'll walk through one of those case studies as well, it is thread director by which we provide that input to operating system. We have also done, expanded our coverage. Both Steven and Arik talked about it. Today, if you look at our laptop usage, what you and I do or what the college and high school kids are doing, they're multitasking, right? There are browser windows open where maybe there is some streaming going on, there's gaming, there's content creation, productivity usages, AI running on any IP. It might be some of the AI runs on CPU as well. There's big percentage of that. So with all of this, we have expanded our use case coverage to do any sorts of thread director recommendations using training that is done with busy use cases. We had to evolve with the evolving use cases that we are seeing, right? So that's one of the things that we have done. And then, of course, with the compute tile P-cores, low power island, compute tile E-cores, low power island E-cores, all of these cores provide feedback to operating system. So we had to make sure that they work well together. They're looking at telemetry, they're providing right feedback to operating system, and all of these cores are working in unison. And last but not least, all these things that we talked about, that tied to OS containment zones. Microsoft launched this feature last year with Lunar Lake, right? If you remember that, we had about 3 containment zones that we talk about. One is efficiency zone, you're seeing at the bottom of the slide on the right side. The efficiency zone is where we have our low power cores. So if you look at Lunar Lake, our LP core sat on there, Panther Lake, same thing. Then we have hybrid or compute zone. In case of Lunar Lake, we had the P-cores on that because we didn't have any E-cores on the compute tile. In case of Panther Lake, one of the SKUs that we have, where we have 4 P-cores and 8 E-cores, they all sit in the hybrid or compute zone, and we'll look at some of the case studies of that. And when we are running multi-threaded operations, like content creation, some of the gaming cases, etc., we have all cores available. We use our LP E-cores, they give us enough performance. We use our compute E-cores as well as P-cores, and we maximize our throughput. So before we go into examples, let's talk about some of the scheduling evolution that has happened. When we talk about Raptor Lake was monolithic die. Both P and E core sat on same ring, same uncore. So in that case, it made sense, even from efficiency purposes, to start from P core first or performance core first scheduling. That was our kind of way to kind of do our scheduling in Raptor Lake timeframe. As we moved towards Meteor Lake, where we started our low power island journey, we had 2 cores there. It was our first step in that direction to get all the software ecosystem lined up, operating system enhancements done, etc. We started on some cases, like in unplugged DC cases, start from the most efficient core, which is the SoC E-cores, and then when either operating system determined or hardware indicated that, hey, I have exceeded capacity of these cores or I need more cores for concurrency scenarios, we went down to the compute complex, went to the E-cores and then P-cores. Same thing with Lunar Lake. Now, Lunar Lake had 4 LP cores on the low power island. And that really worked to capture a lot of situations or scenarios in there, still giving good enough performance on that, right? And then when we wanted that snappy, quick responsiveness user experience, we may move to the P-core, the compute complex P-cores that we had. Now with Panther Lake, we are combining efficiency that we had on Lunar Lake and performance that we had on Arrow Lake and Meteor Lake timeframe, where we are starting with LP cores on some configurations. There are still cases where we start with performant cores, but in a lot of common configurations, such as DC Unplugged, we start with LP cores and then move up. Now, it also works the other way as well. So let's say that you started some task and that needed the compute complex, right? If that task is done, we move back to the efficiency complex to provide that efficiency benefits to end users. So let's look at one of the examples on Panther Lake with scheduling. This is Teams video call plus the Microsoft effect package, the AI effects that are running, right? As you can see, our LP cores are very capable here to keep the work contained you can see that on the bottom chart where we have some of these green activity, that's where 4 LP cores are busy, they're doing work that teams need and the MEP needs. Even though there is NPU activity in here for the AI usages, there's still a lot of activity that AI needs to be preparing data for IP on CPU side. And all of this work keeps contained. It delivers the FPS needed by teams running at 720p. We don't drop resolution or anything, and we are able to keep the work contained. We deliver efficiency because we are able to keep the performance cluster in a low power state, in C states and things, and that gives us benefits on efficiency as well as delivering the performance it needs. Now let's take a look at more demanding CPU usage scenario. This is Office test in Procyon Office productivity workload. What you can see, the brown bars that you see in the picture are where the office work starts. There's some other work that is happening on the low power island as well. But in this case, what you can see in here is we are basically using efficiency cluster. This is DC unplugged case. We are using efficiency cluster to start our work on that. And then when hardware sees that, hey, you can get benefit from using the performance cores because you exceeded the capability of the efficiency cluster, it provides those hints to operating system via thread director. Operating system also has containment thresholds and things like hetero increase, decrease to PPM packages, and it uses this information to move the work to P-core when that snappy user experience is needed. And once that operation is complete, it moves back to LP cores to give the performance back, to give the efficiency back, right? This shows a good example of using our P cores when we really want that user experience. That's what Steven was talking about. There's a reason why we have our P cores, because we want to maximize performance when the user needs it. Now let's look at the third example. This is all multi-threaded, right? Cinebench is one of popular examples, benchmarks that a lot of people look at and use. The beginning 4 or 5 seconds of this workload is, the benchmark is starting. There's some single-threaded, limited-threaded activity, so you see that on there. But once the benchmark reaches empty multi-threaded stage after that, we go ahead and use all cores. There's no delay in opening up cores or anything. Hardware recognizes that all cores demand is needed. OS recognizes that, and all cores are available. So I want to also talk about a little bit on handling, because we are introducing new latest and greatest graphics on this architecture. How are we doing handling games, right? Now, TAP is going to talk about innovations in graphics, such as our graphics intelligence bias control that our graphics driver does. But I want to talk about scheduling. Okay? So this is a DirectX 12 control game that we have. And you can see that I'm showing GPU utilization in here. You can see that for most of the part, it's 100% GPU utilized. Now, it does drop utilization in between, but mostly it's GPU use game, right? Now, what you're seeing here is CPU side of things, how it looks in AC best perf case. If you look at AC best perf, the intention there is to maximize the performance, right? So we start from performance cores, and then very quickly, if concurrency demands, even for millisecond level of operation, we go ahead and expand into added E-cores that we have. So you can see that in between the middle portion is P-cores. 2 primary game threads are running on P-cores. And then other worker threads, supporting threads, they are running on E-cores, they're expanding, etc. Because this was GPU utilized, one of the optimization that we have done, is taking hints from our graphics driver, which is the IBC that TAP is going to talk about, and some of our power management optimizations that we have internally to come up with an improved scheduling case where we actually, when we are GPU bound, let's start from E-cores. So you can see that on compute complex, we are working in hybrid zone because there's enough concurrency. 4 threads cannot fit it, so it's not on efficiency zone. So we are working in compute complex. We start from E-core. We try and keep the work there as much as possible. And we only go to P-core when we exceed capacity. This is the example where, using OS containment zones and some of our graphics driver hints and our power management, we are able to deliver 10% better frame rate because we are making power headroom available to graphics. We are taking advantage of our E-cores on compute complex, the shared caches, and we are able to give extra performance in here. And this is really, I mean, I'm excited about such innovations we are able to bring to market so that we are able to deliver greater FPS and greater performance for our end users. Now let's shift gears a little bit and talk about system software and firmware power management optimization we have done in Panther Lake. So here is a 1,000-foot view of how power and performance management stack works. At the top level, what we have is OEM mode selection, right? So if you look at it, operating system offers basic modes. We'll go through some of it in the next few slides. There's best performance mode, balance mode, best power efficiency mode. I'm talking mainly about Windows ecosystem since that's big in PCs. But at the same time, that OS also gives flexibility for OEMs, such as OEM ABC, can create their own power policies and set it on the platform, right? And they can do it via PPM. We have our own platform software where this is Intel Dynamic Tuning Utility. It lets customer choose, hey, I want more efficient side of settings or more performant. And there's a degree of variance in between, right? You don't get to pick just two defaults, but you have variance in between that you can pick from depending on their particular design, et cetera. And all of those hints get passed to SoC via interfaces that we have created, so that we know what's the platform intent. Is it performance? Is it efficiency? Is it more towards performance, more towards efficiency? We want to know all of that so we can do optimizations. If any changes to core scheduling and things that we need to communicate to operating system, that is done via thread director table. And then OS uses their own goodness, this information to schedule on SoC. So let's talk a little bit about how this platform software and PPM packages work together, right? PPM is a standard interface that Microsoft publishes for any customization for scheduling, such as you can select core parking, core scheduling order, you can select containment zones, etc. And it's a well-defined, documented interface that we have. Using customer input from that interface, as well as the platform intent that is provided by our platform value-added software, hardware combines this information to take all the input about what's the optimal PNP benefit that we need to give. If you look at partner inputs, we also provide options to maximize power and performance. This is the sliders that I talked about in the previous slide, where OEM X can choose that I want to maximize. They might have different designs, so they might be shipping one gaming laptop where performance is the key, or they might be shipping a commercial laptop where they want to manage efficiency better, and we give them options to provide us that information, right? And then we also give them options to manage all of these via PPM interfaces that Microsoft has documented. So this greater flexibility and the optimal points they can choose based off of that gives us information about their intent, and we can manage and optimize our SoC. So let's talk a little bit about traditional OS power management options that we get. So if you click on your battery icon, everybody's familiar with it. There's balance mode, best power efficiency, best performance mode, etc. It's good in a way that it gives a base to start with, right? This is very common. People have used it in the past. But if you are building something and compiling something, then you have to manually move it to best perf mode to finish it faster. Or if you're doing browsing or Teams call and you want to improve efficiency, you want to manually move to best efficiency mode, right? So what we have done in Panther Lake is something called as Intelligent Experience Optimizer. So this is combination of our Intel value-added software, which is dynamic tuning utility, along with the goodness that we have built in our firmware optimizations to basically say in balance mode, if the customer is choosing balanced, I am going to automatically move to provide more performance when SOC sees that the more performance is needed because I see resources being utilized. There's no identification of binaries or anything. It's purely load driven. When I see that I need more performance, it will move there. When I see that I need more efficiency, it will move there automatically. This is one of the innovations that we are really excited about because that helps us, and I'll show some data in the next slide. So if you kind of look at, Arik talked about it, AC to DC performance delta, right? On DC, we don't have to limit ourselves to lower performance just because we have to save efficiency. If we are able to do dynamic optimizations like this, we can still deliver good performance in DC, closing that AC to DC delta. But when the end user is running more power type of or efficiency type of use cases, we can still deliver on that efficiency as well. And using this optimization, you can see that on Procyon, office productivity, or Cinebench ST kind of work use cases, sustained and bursty, we picked 2 examples. We are able to deliver 19-20% extra performance. We are really excited about this feature because that gives us, ability to scale dynamically what user is going to see. So in summary, we have built Panther Lake. We are excited about. I can't wait to get my hands on one. You heard from Steven and Arik. I'm in the same boat. When Panther Lake hits market, I'm going to buy one for myself and my kids as well. But at the bottom layer, we have all these great IPs, right? We have Cougar Cove with a lot of IPC improvements. We have Darkmont, same great improvements, low power island and things. Then we have SOCs, right? 2 different combination of hybrid SOC combinations from Core's perspective. I know graphics adds one more layer there. But we have 4 P-cores and 4 LP E-cores configuration. Or we have 4 + 8 + 4, where we have 8 E-cores on compute tile to deliver multi-threaded performance, right? So we have those. We have scheduling enhancements that we have done internally, co-designed with our operating system vendors, such as Microsoft. Very excited to bring out those to the market, to the end users. Simultaneous execution from all core types to provide data to operating system to help assist in enhanced scheduling decisions that happen. And last but not least, software is a very important part of this, right? We have fine-grained power management that we do in our firmware. And firmware really gives us flexibility to add new innovations after the chip is designed. We don't need to wait for 2 years, 3 years to take it out. We can take it out and make it production very quickly. And that's what the work with Arik's team that happens to bring the goodness out. And then we have platform software, value-added software. We give hooks to OEMs if they want to write their own platform software, as well as Intel software to maximize this further. And with that, I would like to call on Tom Peterson to talk about GPU and NPU. Thank you for your time.